Okay, good afternoon, everyone. Welcome to today's colloquium. I'm very pleased to introduce Dr. Kate Helmstedt from Queensland University of Technology. Kate studies conservation, combining ecological and economic factors across a range of application areas. Kate received her PhD from University of Queensland. Following that, she took a postdoctoral position at UC Berkeley before coming back to Australia to join Queensland University of Technology, where she holds a DECRA. And some good news this week, she has been promoted to senior lecturer, so congratulations for that.
Thank you.
For everyone else, we are going to record this talk, so if you don't wish to appear on the recording, just keep your microphone and camera muted. At the end of the talk, I'll open up for questions and let people unmute themselves for questions. In the meantime, if you want to ask a question during the talk, you can put a message in the chat, and we can do it that way. With that being said, Kate's going to talk to us today about better ecological decisions with mathematics, and take it away.
Thanks, David. Yeah, so 5:30 last night, I found out that I got that promotion. And at the recent ANZM conference, I had bought a $100 bottle of wine and put it aside with the word promotion on it. So I drank that last night in isolation. So if I seem a bit dusty today, it's because I am. So thanks, David, for inviting me to give this colloquium. Of course, I agreed in a world where it would have gotten me a trip to come see you guys, but this is good too. So yeah, I'm going to be talking today about making better ecological decisions with mathematics. And so I'd like to start, as always, with an acknowledgement of country. So I acknowledge the Turrbal and Yagara people as traditional owners and ongoing custodians of the lands where QUT and my home now stand. I recognise that these lands have always been places of teaching, research and learning, and I pay respect to their elders past and present, as well as their laws, customs and creation spirits. And very importantly, I'm grateful for the invaluable role Aboriginal and Torres Strait Islander people play within our QUT community. So Zoom is really hard to give a presentation, and it's really hard to listen to a presentation over Zoom. I know that. It's also Friday of the last teaching week of semester for me and the second last for you guys. And I'm increasingly realizing I have no idea how my students listen to me each week for 2 hours over Zoom. So credit to them. But what that means is, rather than kind of going on a really deep exploration throughout any projects in this talk, I'm going to kind of give a smattering examples of how we're using mathematics to improve ecosystem management in Australia and globally. And so really my objective of this colloquium is, if you walk away thinking like, maths is helping society in a way I didn't really think about before, then I'm happy about that. So I work in the world of ecological decision science, and as with most difficult decisions, we're living in a system where we have limited time and money and personnel, and we want to conserve. Basically, all of our objectives in this field are about kind of conserving or preserving endangered species, critical and collapsing ecosystems, and ecosystem processes. But in the same context, like working in that same system, we're really increasing the needs that we're getting from the environment. So as our human population skyrockets, that means that our demands on the ecosystems are getting much larger. So we need more food, we need more land, water. We have increasing needs for recreation and storm protection from the environment. And so what that means is that we're really faced, all these things contribute to mean that we're faced with really difficult decisions in environmental management, particularly when focused on biodiversity conservation. But of course, that makes it a perfect candidate for a place where operations research, decision science, and optimization can kind of swoop in and offer some real opportunities to improve our management of these systems. And the way that I personally think about conservation decision science in these ecological systems is I think about kind of 3 really broad categories of management that we might be coming at these systems with. So we're always trying to think about conserving more species for less money, or some version of that. But the way we can actually attack the system and the levers we can pull can be very different. And I think of there as being three broad categories: top-down control, bottom-up control, and what I am currently tentatively calling disconnected control, but I'm not sure if that necessarily captures exactly that, but I'll get to that third. So if we think about top-down control of environmental systems, so this is a world where we think about, where we assume complete control. So we're kind of imagining that there is a benevolent dictator that makes decisions in this system in the best interests of the entire system, and there is like a truth to the maximum utility that we can get out of environmental systems, and that utility is kind of correct and agreed upon. And so we're still limited by constraints, and actions can still fail. So we can recommend actions that just don't work out. So there's still that uncertainty and stochasticity. But in this top-down control world, we assume that if we take an action, or if the decision makers take an action, it will be performed. And so examples of this from my group's research. So for example, we can think about where should we put things like national parks and reserves, and we can use spatial linear programming to attack problems like that. We can think about what projects we should choose from a suite of options. Should we do this for this species or something else over here for another species? And that is an example of project prioritization, which we can attack, you know, as if it's a knapsack problem. Within this kind of top-down control world, we can also think about how we can produce more for less impact. So be meeting those needs of society while kind of minimizing those localized impacts on the system through things like supply chain optimization. And I have a student currently working on kind of thinking about how trade networks might be able to be managed in order to achieve this, in order to achieve more for less impact. And the other type of top-down control problem that we think about is when we should act when making sequential decisions. So in ecological management, we're not always just making a single decision like build the national park there or over there. It's a series of repeated decisions over a very long time, because we tend to want our outcomes in perpetuity rather than kind of just achieving something once. And we can attack those types of problems with techniques like stochastic dynamic programming. And I'll just talk about one kind of example of vignette here that does this kind of sequential decision-making problem. So when should we do things in these environmental systems where we here is that top-down control is that benevolent dictator? We assume that they will be able to do what they want to do. So this is a project that I worked on with Perth Zoo, with interest from the Queensland State Government. Bridled nailtail wallabies are a critically endangered species on the east coast of Australia. They're very cute, so people care about them, which tends to be the pattern. And they used to be kind of pretty broadly distributed in that blue area across the east coast of Australia. But with kind of habitat loss and ongoing pressures from people, they've really contracted their, we've contracted their habitat into these like three very small orange dots, or four very small orange dots spread across that landscape. And so part of being critically endangered is having few very isolated populations. And so one thing that ecological managers are really interested in doing for many species, and particularly for these bridled nailtail wallabies, is like reintroducing them into places they used to be, by building new populations there. So establishing completely new ones, because they're not going to be able to travel from those small orange dots to naturally repopulate. And so this question that Hugh Possingham and I attacked is, if we've got multiple potential locations in a landscape that we might be able to create a population, plus some reliable source population of individuals, how through time should we be distributing those to build those populations for like the greatest certainty of outcomes, certainty of populations by the end of that time? And this is a it's a sequential decision-making problem because rarely would we ever be handed a huge population. Like, you'd never be handed 100 wallabies and told, put these somewhere and establish a population. When we're thinking about endangered species, we get a few every breeding season, and we need to figure out what to do with those. And so it really becomes a decision that has to be repeated many times throughout the time horizon. And so we constructed a kind of matrix population model for these bridled nailtail wallabies that basically boils down to a transition probability of growth from any specific state to another state of these wallabies in a single one of these patches or populations, and then combined across the entire system. And by formulating it in that type of model where it relies on these transition probabilities, it allows us to formulate the whole question as a Markov decision process. And so in a Markov decision process, we make decisions kind of at fixed time points, and those decisions can affect how the system changes and grows over the time. And so in this particular model, there's this 4-month time step. And so we assume that every 4 months, the wallabies that are already released into the wild will breed, kind of generating free individuals for us that didn't cost us anything in our allocation. The captive population, or the source population, also breeds and produces some additional individuals that we can then release into these populations. So every 4 months, we get 4 or 8 individuals that we can allocate to one of these populations. The actions that are available to us when we're thinking about this type of problem is we can open new sites, we can release to any of those populations that we've already established, and then we can kind of look at a population and say, we are confident enough in this population to be self-sustaining that we can walk away from it and kind of put our management efforts somewhere else in the system. And so it becomes this question of how do we do those actions and spread those actions between the populations over kind of longish time horizons, so say 50 time steps time horizons. And because we've formulated as a Markov decision process, we're able to use stochastic dynamic programming to come at that question to find an optimal schedule. And stochastic dynamic programming is a formal approach that allows us not to just optimize our system now. So not just say we want, like, what should we do to get the most wallabies today? And not just to say kind of myopically, what should we do to get the most wallabies next breeding season, say, but what should we be doing to maximize the amount of wallabies we have in our system over that entire time horizon? So it allows us to make short-term bad choices, like spending a lot of resources and time on opening a new site, because we have full visibility of this whole time horizon that we will later kind of make back that utility from that myopically bad choice. And we do this through the Bellman's equation, which kind of formalizes this idea. So there's some reward that we get, there's some utility that we get for having a lot of wallabies in our system. We're happier with more wallabies and sadder with fewer wallabies. But then also thinking about how this stochastic system will unfold or is expected to unfold over that time horizon, so that we can really think about these like winding stochastic trajectories through time that lead us to higher populations eventually, and allows us to kind of add up all of those immediate rewards that we get over that time. Bellman's equation, we think about it as being a forward planning problem. We think about, okay, well, we know where we want to get, and we know where we are now, and we want to take steps forward through time, but we solve it with backwards iteration. So I solved this problem numerically in MATLAB, and what the output of stochastic dynamic programming, which is critical for when we're thinking about, okay, this is a real environmental system that someone is going to want to manage. What we create here is, instead of being like a really complex decision rule, what we create is essentially a lookup table which allows the managers to say, okay, I have 5 individuals in that population over there, I have 2 there, and this population's not started yet. I'm going to look that up in my table and know with this amount of time left what my optimal decision is, given that I will be accumulating individuals throughout time as well. So it allows us to take a really complicated problem and make it an incredibly accessible decision to use in the real world. And so we basically developed this optimal schedule for how you might start with none and end up with 3 self-sustaining populations. And so what we found is that you'd open one site and release some individuals there. Then you open your second site and you release to whichever population is smaller until they hit some critical threshold. So there's some population threshold that says, okay, those ones are good enough. And then we'll spend our time then, our efforts, also opening that third site. And so eventually we end in this system where all of the sites are open and we're releasing just to whichever one can use the new releases most effectively. But this is an incredibly unsatisfying schedule, because of course you would do that, but in the real world it costs something. It costs something to keep populations open, and so it's unrealistic to just continually be topping up these populations. And of course that's going to be good, because you're always just in perpetuity looking after the populations. And so we thought, okay, to kind of step this towards a real problem that people have in environmental management, what kinds of costs might be incurred by having these populations open and constantly releasing to them? So the first thing that we looked at is financial cost. So it costs you something to have a site open, to be constantly releasing somewhere. It costs you something, it costs you some of your resources, and so you don't have those to spend somewhere else. And so what we found when we examined the same system with that kind of cost is that it's the exact same pattern of opening. You open one, you release a little bit. You open the next one, you release a little bit to either one of them. You open the third one. And there's some time in the middle here where all of them are open and you're bolstering all populations. And then once you're confident enough in the size of them, you can close those release programs down. And so that's comforting, because we see what managers want, which is you don't have to continue doing these things forever. But from an ecological perspective, one of the costs that people are really interested in is not just a financial cost, because in some ways those are a bit more flexible. But if we're having to go and kind of count the individuals in these systems and constantly be releasing to them, there's a question of whether that has some kind of demographic cost. Is that hurting those populations each time we have to go and do that? Does it hurt the populations just a little bit to have them be open? And so the next thing that we examined was, what if there is this demographic cost, which was a small increase in the mortality rate, to being one of these open and constantly releasing sites? And what happened is, when you think about that kind of cost, the kind of structure of your optimal solution completely shifts. You actually never want to have them all open at the same time, because you're wasting individuals in that time instead of accumulating free individuals in that time. So it becomes kind of open one, release a bunch of individuals until you're happy with it, close it and move on. So that was kind of both the specific recommendations for Bridled nailtail wallabies, but also our broad kind of rule of thumb style outputs from that top-down control project. But of course, all of this only works, like it still has this stochasticity in it, it still has populations potentially going up and down without you interacting, but when people release things, it happens. And that really characterizes those top-down control problems. But in biodiversity conservation, we're often trying to get people to do what they might not want to do. And this is largely driven, largely driven by the fact that a lot of these species and critical ecosystems actually exist on private land. So in that Bridled nailtail wallaby example, we're saying, like, there's 3 places where we can just generate these populations and it's great, but those have to be publicly owned land. You can't just go and establish establish these populations on someone else's land. But the existing kind of capacity of biodiversity that we have globally, so this is an issue everywhere, it tends to mostly be on private lands. And so what that means is that we need people to manage their lands economically suboptimally, right? So they have some economic or otherwise, they're making some decisions about their land, and it's normally not driven by species conservation or ecosystem service conservation. And so we're trying to find ways to get people to do things that's economically suboptimal for them. And the mechanisms we have, the levers that we can pull in order to do this type of bottom-up control, is we can make laws, we can do education campaigns that might change people's internal utilities, we can design incentive schemes, or we can introduce market-based mechanisms that help this to happen, that flip things from being economically suboptimal into being economically optimal for landholders to do. I'm going to talk about a couple bottom-up control examples just pretty briefly, both incentive schemes and market-based mechanisms. So first of all, designing incentives. So there's this kind of recent-ish, in the last couple of decades, global fad called payments for ecosystem services, which is acknowledging this issue, right? So it's saying, okay, well, if it's economically suboptimal for you to have some habitat on your land, then we can pay you a little bit of money to preserve that habitat on your land. But the problem is these budgets are very fixed. So there's a certain amount of money that we can spend for many different landholders in the system. And so if your objective is to increase native habitat across multiple landholders, and your action is that you can pay those landholders, then the question is how can we best allocate those limited funds to get not only the actions that we want, but the largest impact of those actions as well. So get landholders to take stronger actions on their land. And this is a project that I did with Jane McDonald, who is now at the Queensland State Government, where we were really thinking about this from a kind of competitive standpoint. If there's a fixed budget, it forces the landholders basically into a kind of constant sum game. If I earn a little bit more of that budget and you're pulling from that same budget, you get a little bit less of that budget. And so my payoff depends not only on what I do on my land, but it also depends on what you've done on your land if you're my neighbor and part of this scheme. And so in order to model and predict the landholder response and therefore the environmental impact of these potential allocation incentive allocation schemes, we modeled this as a competitive game, and we in this project just looked at two neighboring landholders. So both landholder has their individual selfish objective to maximize their profit. That's going to come from the agricultural profit on your land, plus whatever payment it is you're getting from the scheme. The landholders are going to share in that total budget. And so we modeled it as a competitive game where your payment depends on the other landholder's action, and we just numerically determine the Nash equilibrium because there's a lot of actions in a lot of actions available to you. And so what we did is we used this competitive game model to not to optimize, but to predict what the landholders will do when they themselves are economically optimizing. And we can use that idea of almost like scenario modeling, where there's individual economic optimizing that system. We can use that to examine different approaches to how we might allocate the funds. So each landholder has their own economic objective, but we're assuming there's an objective coming from on high, which is to have the most habitat in the system. And so we examined three, or there's more in the paper, but three ways that we might allocate these funds. So first of all, what's normally done is just payment per hectare. So if you have if you set aside 50 hectares on your land for koala habitat, you get 5 times more money than you would have if you had only 10. We examined pay per hectare relative to farm size. So this takes into account that you and I might be in a competitive game, but I only have a very small farm, and you have a very large farm, and so arguably it's easier for you to do more than it is for me, and so like a relative payment to our farm sizes. And then we examined pay for change, which is instead of someone coming in and looking at our land and saying, you've got 50 hectares of koala habitat, so I'll give you, this share of the budget, saying, okay, you used to have 49 hectares of koala habitat on your land, now you've got 50, so we're going to pay you for that single hectare increase. And then we compared conservation outcomes for the resulting native habitat areas. So we compared really not just the habitat areas, but what it means for populations on these landscapes. So what we did is we examined, these are simulated landholders and simulated landscapes. And so what we looked at is we explored a pretty broad parameter set here of, on the y-axis is basically the profitability of the farm. So if you have a very profitable farm, you're less likely to want to put aside any native habitat because you have to get paid a lot more for it to be worth it. And then on that x-axis, we've got initial population size of the koalas on your land. So if you only have a couple, then it takes a longer time to increase that population. So there's a delayed response to the new habitat. So yes, there's a scale here there's a color scale here, but what is most important is that where this heat map is white, that's a parameter combination where we actually see, as a result of this payment scheme, we see a population decrease. So if we're doing a set price per area, it's actually, once you get above a certain profitability for your farm, you're actually never seeing a population increase, and in fact you're seeing a population decrease, just because it's so much more profitable to keep clearing for agriculture. If we look at it relative to your farm size, it's a little bit different. It depends a bit more on your initial population size, but we're still seeing this these massive swaths of parameter space where you're just not achieving anything despite the fact you're paying for it. But if we do pay for change, we're seeing that actually it's much less susceptible. It depends much less on the profitability of your farm, because it actually only takes very small changes to get a big chunk of the budget. And so this competitive aspect of the interaction comes in more. For me, it's very easy and cheap to set aside just 1 more hectare. And if you do nothing and I set aside 1 hectare, I get tons of money. And so of course that means that, and so you will increase yours to a certain amount. And so you see more of a competition between neighboring landholders to be achieving these cheap per hectare or a high budget return per hectare changes in their landscape, because you're paying them to do something instead of just paying them to have something that they always had. So the other example, sorry, I wrote designing laws there, but it's actually an example of a market-based mechanism. So in that game theory project, there is a scheme or a government who's injecting money into this system and saying, we're willing to pour this money in to get these outcomes. Although it's increasing in prevalence. It's not that common for governments to have a lot of money to kind of pour into that type of scheme. And so what's another option here is to have that income generation coming from the system and from the landholders itself. And this is a project that I did with Matthew Potts at UC Berkeley. And it was focused on biodiversity conservation in Brazil. And in Brazil, there is a lot of, critically endangered species, a lot of critically endangered habitat, but there's also a lot of legal and illegal deforestation on both public and private land. And what's critically important about the deforestation that's happening in Brazil is that there's non-linear impacts of habitat destruction. So when someone clears 1 hectare of habitat, it's not twice as bad to clear twice as much because of these non-linearities. So what happens is when habitat is cleared, it results in smaller forest fragments, and each one of those smaller forest fragments has lower local carrying capacities than it would if they were all together. There's decreased dispersal if they're very far apart. And there's what's called negative edge effects, which is basically species don't do as well if they are in a bit of forest that is basically abutting agricultural land. So species do much better when they're in the center of a large piece of forest than on these edges. So the more edges you have, the lower your edge to area, higher your edge to area ratio is, the worse off your species are, regardless of the area itself. So in kind of response to these complexities and to the critical nature of conservation in Brazil, the Brazilian government has implemented a Brazil Forest Code, and that requires every single landholder across the country, every agricultural landholder of a certain size, to set aside a proportion of their land for native habitat. And it varies a lot, from 80% in the heart of the Amazon. So if you have agricultural land of a certain size in the middle of the Amazon, 80% of that legally has to be native habitat and cannot be used for agricultural pursuits. Down to 20% in tropical savanna areas. And if we were to think about what complete compliance with this law would mean, it would be a really diffuse landscape of that habitat. So everyone would have a little bit of the habitat, but it would be spread pretty evenly around different ecoregions. But you'd have a really certain area of forest. So tick on the fact you've got a lot of area, potentially cross on the fact that it's really diffuse and not clumpy. But that's if everyone's complying with this law. And the fact is, in Brazil, there's really high levels of undercompliance. And what that means is a lot of people aren't meeting those thresholds. They have cleared more of their land than they are legally allowed to. And so a proposed or partially implemented change to Brazil's forest code is to allow trade of these limits. So this is a market-based mechanism that says it's possible that I have cleared more than is legally allowable. I've cleared too much of my land, but you actually have extra on you for some reason have cleared less than the legal requirement. So you have more habitat on your land. If there's enforced compliance of this law, over time, I will have to reforest up to that threshold, and over time you will deforest down to your threshold, if we assume everyone's economically optimizing. But what this trade will allow is I can pay you a certain amount of money, to be determined by us. I can pay you to hold that excess in perpetuity. So you now are holding my legal requirements, and I have brought myself into compliance with the law. And this is like, we tend to think that schemes that allow people to buy themselves out of the fact that they broke the law, there's a certain distaste for that. But the question we were asking here is, like, is that distaste just because it sounds icky? Or is it possible that because of these non-linearities in response to habitat loss, is it possible those non-linearities actually mean that this thing that feels a bit icky might actually end up being better in some landscapes in Brazil? And so what we did is we modeled two types of landholder, or landholders' responses to these two different options without the market mechanism and with the market mechanism. So if you're not allowing any trades, we model each individual landholder in simulated environments. So simulated landholders in simulated environments, we assume that they themselves are each maximizing their own profit from agriculture, and what they can do is reforest parcels, deforest parcels, or do nothing if they're already in compliance. And we can do that modeling really easily across the landscape, because we can just do each person in isolation and predict what their farm is going to look like, and then stitch it together to see for the whole landscape what that means. But when we allow trades, that we add an extra kind of decision variable here, which is how many of your parcels will you be trading? Maybe you're selling the rights, maybe you're buying the rights. And it means that we need to assess the landscape as a whole. So, so we modeled economic maximizers that are maximizing their agricultural profit plus their outcomes from the market. So each individual landholder has their own maximizing objective. They have their own constraints, and at the landscape level, how we simulate the trade in this project was we set the market price based on the supply and the demand, so the over compliant land and the under compliant land in that landscape, and what the potential agricultural productivity is from those. So if people only have very cheap land to sell, but everyone has really expensive land that they want to spend money preserving, then you'll have a market price in response to those those supply and demand curves. So what we did then is simulate, so predict across a whole simulated landscape what the outcomes will be, what the actions of all the landholders will be, and then assessed the biodiversity value of the entire landscape all at once by thinking of the landscape as a graph or as a network. And so where gray here is is habitat, and white is cleared land, we can think about the connectivity of little patches of these landscapes as little connected subgraphs. And that allows us to then use all of the existing graph theory metrics to assess things like connectivity and edge to area ratios and things that we care about in landscape ecology. So just give you an example of one of these simulated landscapes. So this is a simulated landscape that has brought itself into compliance with the law. So where every individual landholder, and I think this landscape here is like 200 or 400 simulated landholders, each one of those has met a 50% threshold by clearing their least productive land. So they're each optimizing themselves. And so what we see is what we predicted, a really diffuse landscape of the grey habitat. I've highlighted two things that people care a lot about in landscape ecology. So the yellow is the patch that has the lowest edge to area ratio. So animals like being in the middle, don't like being on the edges. That yellow bit's the best for that. And the one highlighted in green is the largest contiguous patch of habitat, which is has a higher carrying capacity. If we think about the exact same starting landscape, but allow the landholders to have played out this market, then this is what that landscape will look like. So we see what we expected, really clumpy areas of habitat, and also really clumpy areas of agricultural land, which is probably driven by agricultural price. And so the question here is that trade-off worth it? Like, are we doing better if we allow the market to, if we enforce individual compliance? And what we did is simulated a lot of different landscapes with a lot of different landscape assumptions. So each colored bar is a different assumption about the landscape, a different assumption about how the cost is distributed, a different assumption about how clearing has already happened in the area. Each cluster of bars is a different kind of graph theory or kind of landscape ecology metric. So probability of connectivity, maximum fragment size. The height of the bar is saying how much better that metric performs if you allow the market to, if you force individual compliance. So anytime that number is positive, it means that the market is better for biodiversity. And so what we were really shocked to see is that for a lot of different, for every single metric that we tested, and we tested more than these, including economic productivity, it's better to allow that tradable development rights market than it is to force individual compliance. When there's a single habitat, we also explored what if there's multiple habitats in that landscape, and it degrades how much better it is to have the market, but it doesn't erase how much better it is. So it still is better that the markets, that market that felt icky, that allows people to buy themselves into compliance with the law, turns out when we remove ourselves from that and assess the biodiversity outcomes, in many of these cases, is better for biodiversity. So those were a couple of examples of kind of bottom-up control, and you can see similarities between them, right? Like we're trying to get people to do things they don't want to do by trying to understand how they will respond to overarching controls that we might do. And that kind of brings us a little bit to this like third category that I'm starting to see arising from a lot of different projects and problems that I'm working on at the moment. And I'm tentatively calling it, as I said, disconnected control at the moment. And so this is the type of problem where we have no direct control over the actual ecological system. We only have control over mechanisms in a more complex remote system that's going to affect how people act in that kind of lower level decisions or direct control decisions. And this is driven by, or one strong example of this that's kind of coming out of my current work is thinking about the optimal research and development of different technological interventions. So basically in these biodiversity conservation worlds, we often don't have the technologies that we need to achieve what we need to achieve. It's not a matter of doing them better through time or putting them in better places in the landscape. We just straight up don't have the technologies. We can't achieve it yet. And an example of this is the Great Barrier Reef. So Great Barrier Reef is, experiencing massive degradation and decline in quality, in area, in ecosystem function due to climate change. And so what we will need to do, other than stopping climate change, which is absolutely critical, but as a stopgap to bridge this temporal gap between what if we can stop climate change, something needs to happen in the meantime still. And so technologies that can increase the climate resilience of the reef are going to be needed because we just currently don't have them. And so the question is right now, like with that really removed perspective of technologies, which technologies should we spend a lot of money and a lot of time to develop? Kind of given that in this complex system, and the nature of developing technologies or the nature of research in general is you might pour a lot of money into something and it just never comes to fruition. And so we want to be pretty sure that in 10 years we have something that is going to build climate resilience on the reef. In 5 years it'd be better. What if that 5-year delay is really critical? So there's all these uncertainties that we're really at a really long arm's length away from with the decision that we have available to us now. So how do we like make that decision to manage the risk over this long time horizon? And so what we really have there is like this disconnected control. So we can plan what technologies might be available in 10 years, but we have no control today over how it's going to be used or where. And we're putting these technologies in the hands of decision makers in the future who are autonomous and themselves top-down controllers. And so the question is, with this disconnected control question, is will their decisions in the future does that change the optimality of the decisions we make today? Like, do we need full visibility over what those decisions might be in the future in order to really make optimal decisions today? And it's not like I think, I mean, especially for this reef problem, it's not like I think that these technologies are so bad that people are going to like use them to do bad things. But if I really strongly believe, or the stakeholders we work with today really strongly believe, for example, in traditional owner values of the reefs, can I guarantee that whoever's making these decisions in 10 years is also thinking about the exact same objectives? And so there's potential sources of disconnection here. So one of them is different objectives. Will that future, or doesn't have to be a temporal difference, but does that decision maker who's at an arm's length from me, do they have the same objectives as I have? Are they working in the same environment? So has the world changed in that 5 or 10 years so much that their options and the way that they analyze the world is different? And do they have different information? Does the arm's length decision maker know more or less or different about the system that would mean that they might make decisions that would be worse by our standards, and then like erode what we think is the optimal decision today? And this kind of disconnected control comes up in other contexts. So another context in which I'm working on this same sort of problem is if we're thinking about the fact that federal governments need to allocate budgets to local governments to conserve local species. So the federal government doesn't do that much on the ground, but the local governments do. So if the federal government has objectives and they allocate money to different states based on those objectives, do we know that the states are going to end up doing the things that we thought they would? Another example is thinking about CEOs of organizations who have enabled autonomous units. Does the CEO's idea of what the company should do actually match with those lower level decision makers? And presidents, are not able to control whether, for example, governors, for example, open economies, but they can take other types of actions that limit what the governors can do, for example, withholding critical PPE. So we see this kind of arm's length decision making in a lot of different contexts, including biodiversity conservation. And how we've started thinking about this disjoint control is by thinking about using bi-level programming, which already exists. Of course, anytime you think of a cool applied question, don't worry, someone's already thought about it and designed it. And so we're thinking about this now as being kind of a top level decision maker. That's what we can control. And there's some following autonomous decision maker that then acts after we have acted. And so we have some kind of objective function that we are trying to maximize, but so do they, and it's not necessarily the same. And that our actions are going to control what utilities they can get out of the system, and their actions are going to influence how we project forward those utilities. So we have to think about what the actions of that lower level, that following autonomous decision maker is doing. We have to kind of try and predict what they're going to do given their different information and changed systems to think about what our utilities might be with the decisions that we're making now. I have no results. All I've been doing is thinking about this in multiple contexts. I know nothing. Here is where last night when I was writing my slides, I started drinking my $100 bottle of wine. But the contributions I think from this work is going to be, okay, like first of all, bringing this method of bi-level programming into these conservation decision science types of questions. But I think as with the other examples, there's going to be 2 levels of things that we find out. There'll be problem specific recommendations about what you should do in systems and who could collaborate and how that should be controlled, but also broad observations about what kinds of disconnections are worse and can they be managed. Thanks.
Thanks very much, Kate. Okay. Now, everyone should be able to unmute themselves. If anyone would like to ask a question, you should be able to unmute yourselves now or put something in the chat if not. Well, I have a question. Actually, I find this very interesting. One thing in particular, for the first bit of modeling you're talking about reintroducing species, I was thinking what sort of, because if you have like a very nice, the result you had, that's like a very simple thing. It's like you do one, then you move on to the next habitat, and you move on to the next one. Is that, how specific is that result? How specific what sort of data do you need to come up with that sort of result, or is it a general
Good question. So the actual structure is quite robust, we found. So as long as you can model the problem in this type of format, as long as you can build it as an MDP, as long as you have the same structure of having individuals coming every, whatever the time step is, structure stays the same. Open them, have a lot of them open at the same time, and then sequentially close them, or flip if you have a different demographic cost. And that's really nice, because that's actually the level of information that environmental managers want. They're not really looking for the exact critical threshold numbers. What they're looking for is like a general rule that indicates something about the structure. What does change specifically for different examples are these, what the critical population thresholds are. So exactly what population should you be looking for to open the next site or to close them down at the end. That changes.
Right. Yeah.
Yeah.
That makes sense. I think this is a common thing, working out how you've got all this information, how you can make it useful to people to make decisions on the ground.
Totally. And so I think like one of the ways to do that is to, even though as mathematicians we do get these optimal recommendations coming out of systems, we know exactly what these numbers are for this parameterization. I think what I always try and do is like take a step back and say like, okay, the broad observation across most of the parameter space is this or that. Yeah. But it's yeah, absolutely an ongoing challenge, or else we're just talking to ourselves.
Yeah. Does anybody else have any questions?
Sophie, is your question whether this is an ANZM merch bottle? It is, and I'm not using it performatively. I genuinely drink out of it at my desk every single day.
Very good. Represent.
Preempted that question.
Okay, well, let me thank Kate again for your very interesting talk, and we'll finish the recording here, and have a very good weekend, everybody.
Perfect. Thanks, everyone. Nice to meet you all.